All right, this is section 3.3 on optimization. Many problems consist of optimizing a function, and so that's finding its maximum or its minimum value. And one of the principal uses of calculus is that it can provide us a very general technique for optimizing functions quickly. So we're going to concentrate on applications of optimization, and accordingly we will optimize continuous functions that are defined on closed intervals, or functions that have only one critical number in their domain. So most of these applications fall into two categories, and that's the wide range of examples. In this section, we'll demonstrate the power of these techniques. So optimization, again, is finding that maximum and that minimum value. Where that comes in handy is we can find the absolute maximum, which is the largest value on the function of the domain, or the smallest value, that absolute minimum value. These are both classified as absolute extreme values, and it's the value that is either the absolute max or the absolute minimum of the function. And what we're going to learn is how to find those values. All right, so the maximum and minimum values of the function correspond to the highest and lowest points on its graph. So we can also graph the function and find these. So if you look at slide 3, for a given function, both absolute extreme values may exist, or one or both may fail to exist, as the following graph shows. So the first one has both a maximum and a minimum. The second one has an absolute max, an absolute minimum, but no max. The third one has an absolute maximum, but no minimum. And then the third one has neither. It's going to continue rising and falling at both ends of that graph. But what we're going to be able to do is block the function off for a certain section, and then be able to find an absolute maximum or minimum on that section of the graph. And that's where slide 4 is telling us how to do that. So to optimize continuous functions on closed intervals, meaning instead of going from negative infinity to positive infinity, we're going to have set values that we stop at. Okay? So a continuous function on a closed interval from a to b has both an absolute max and an absolute minimum value. And to find them, we have two steps. We're going to find the critical numbers of f in the function. Remember, critical numbers means find that first derivative and set it equal to 0. And then we're going to evaluate f at the critical numbers and the endpoints. All right, and the largest and smallest values found in step 2 will either be the absolute max or the absolute minimum values of the function on that interval. Okay? All right, so I get this to move. We want to find the absolute extreme values of f of x equals x cubed minus 9x squared plus 25x on the function 0, or on the interval 0 to 3. So again, first step is to find the critical numbers. So if we take the derivative f prime of x, we get 3x squared minus 18x plus 25. And I just realized I have a typo because this is not going to factor like we need it to. This should be 15x. Sorry about that. Let's fix that. This will be 15. Now it will factor for us. And you could do the quadratic equation and factor this as well, and get different numbers. But for this example, and for it to match the graph at the end, that does need to be 15x. All right, so when we find the critical numbers, we're going to set this equal to 0 after we find the derivative. I can factor out a 3, leaving me with x squared minus 6x plus 5 equal to 0. And then we factor more. I have 3 times x minus 1 times x minus 5, giving me critical numbers of x equal to 1 and x equal to 5. Now, we're on the interval from 0 to 3, so I do not need x equal to 5 for this example. Okay, if your interval was bigger, you would use it, but since our interval just goes from 0 to 3, I don't need x equal to 5 for this problem. Okay, so step 2 is that I need to evaluate. I need to find f of 0, f of 1, and f of 3. And you don't have to take a lot of time to do this, just plug it in. And we're plugging that into the original equation. Okay, so if I'm plugging 0 in, I would have 0 cubed minus 9 times 0 squared plus 15 times 0, which gives me 0. F of 1 gives me 1 cubed minus 9 times 1 squared plus 15 times 1, which gives us 7. And then we have 3 cubed minus 9 times 3 squared plus 15 times 3, which gives us negative 9. Again, you can plug those in your calculator very quickly. Don't take a lot of time on it. But what we see is we have an absolute maximum and absolute minimum. Our smallest number is negative 9, so there's our minimum. And our largest number is 7, so there's our maximum. Okay? So on this interval from 0 to 3, the absolute max is at x equal, the absolute max is 7 at x equal to 1, and the absolute minimum is negative 9 at x equal to 3. All right, so the maximum and the minimum, when we say the absolute maximum is or the absolute minimum is, those are y values. Okay, so keep that in mind. These are y values, and they occur at an x value. Okay, so hear that language again. The absolute maximum or the absolute minimum is a y value that occurs at a given x value. Okay? Now, if you go to slide 7, you see that the absolute maximum and minimum values may be seen on the graph shown below, and it's important to realize that we found them without drawing the graph. You don't have to draw the graph to find these. You don't have to graph anything. You can find them very quickly by just plugging things into the formula once you find that derivative. All right, but we do see a maximum at 7. Oh, to underline that. A maximum at 7 and a minimum at negative 9. Okay, so the highest point on the graph and the lowest point on the graph. All right, that's absolute maximum and minimum. Now, for this function, one extreme value occurred at a critical number and the other one at the endpoint, at one of the endpoints. In other problems, that can change. Both extreme values might occur at the critical numbers, or both might occur at endpoints. All right, but notice how calculus helped in this example. The absolute extreme values could have occurred at any x values, think about that, any x values from 0 to 3. That's an infinite possibility, okay, an infinite list of possibilities. All the numbers between 0 and 3, not just the integers. Calculus reduced that list to a mere 3 numbers. Okay, so then we only had to test those numbers by substituting them into the function to find which numbers made f the largest and the smallest. So calculus is really helpful here. All right, let's try another example. Or not. Hold on. I'm getting ahead of myself. Sorry, the second derivative test. We did the second derivative test back in section 2. I know that seems like a really long time ago, but we did. The second derivative test is a way to determine whether a function had a maximum or minimum at a particular critical number. The amounts and amounts simply to checking the sign of the derivative at the critical number. Okay, so if you haven't put that on your list of formulas or rules yet, this is a good one to add. So we know x equal to c is a critical number at which f double prime is defined. Okay, if the second derivative of c is positive, we know we have a relative minimum at x equal to c. If f double prime of c is less than 0, is negative, then we have a relative maximum at x equal to c. It's always backwards from what you think. All right. Now I'm actually going to stop this video here, and we'll start with the next example in the second video.